In this video, I'm going to show you some visualizations of different types of waves. The first is a longitudinal wave in which the driving force is parallel to the direction of propagation. So we can see the wave is propagating here, like so. The driving force is back and forth, and the wave is going in the same direction. So this gray barrier is providing the driving force, and the wave is propagating in the same direction. So they are parallel to each other. We call that a longitudinal wave. And this is the type of wave that sound is. So these little dots would be air molecules vibrating. Now we take a look at one particular dot. Let's find one right here in the center, say. And I'll just peep the circle on it. And if you notice what's happening to that red dot, is it's just vibrating back and forth, back and forth. And that little particle is undergoing simple harmonic motion as it oscillates back and forth. And we'll look at this red dot here, and we'll watch the same thing occur. And this one over here, back and forth, vibrating, oscillating around an equilibrium position. Now you can see this results into some areas where the molecules are compressed together. We call those compressions. And there's spaces where the molecules are spread apart. In other words, they become more rare. We call those rarefactions. So down below, you can see it's being tracked along compression and rarefactions. Compression, compression, and rarefaction in between. And of course, we have the wave front moving forward like so. So this is a longitudinal wave and how it propagates, and as well as what's going on with an individual particle. Now, transverse waves we have are more common what we think about as a wave. And here you've got these particles, and they're vibrating up and down. But you can see now that the driving force is in this direction, up and down and up and down. But the wave propagates this way. The wave propagates perpendicular to the driving force. And that's what transverse waves are. Trans means across. So you have this crossing of the two directions in this case. Now we notice there's not compressions and rarefactions. It's that the particles are moving and displacing vertically back and forth. Then we get water waves, which are very, very interesting. If you look at the circle here, notice that circle is fixed to one water molecule. And that one water molecule is traveling in a clockwise circle in the direction of propagation of the wave. Across the top. So again, we see it's a circle. And this is why, as you can see in all the cases we've seen so far, the particles themselves do not travel. It's just the energy is propagated through the material. Even further down with a water wave, the particle is traveling in a circle. And in fact, you could imagine a series of circles of increasing radius being stacked between the small one and the large one, and there's circles in between. And it's when those circles end going down into the water that the wave no longer penetrates. But that's the type of motion with a water wave. Lastly, we have a Rayleigh wave. And the Rayleigh wave, if you notice that particle that's fixed, the orbit it's taking is not a circle, it's an ellipse. And that one particle stays fixed. And so that particle is tracing out the motion of an ellipse. Notice it is counterclockwise. And when we go down further, notice that it's another ellipse, but it is traveling clockwise. So you have these opposing motions going on. And if you look at the geometries, you can see the water wave is peaked, and the Rayleigh wave, or surface wave, is rounded. So produces a different geometry. Now, Rayleigh waves can be earthquake waves. Water waves, of course, are water, liquid waves. S waves are what you may have learned in earth science as a shear wave, an earthquake wave that's a shear wave. And so you can see that if you take a rock and vibrate its lattice in this direction, the energy can spread outward. That disturbance from the driving force can spread outward in this direction. But if you were to try to do that with water, try to jostle it up and down, it wouldn't go perpendicular. It would only go in the direction you're pushing it, which is P, or a primary earthquake wave. It goes in the direction. And one of the nice things about this is that if you are a geologist or a seismologist, you can tell what type of earthquake it is, whether rocks were colliding or whether they were separating, based on what we call first motion studies. When the seismograph station is, say, in that circle, when it first arrives, do you get a compression or a rarefaction? If it's a compression, then the earthquake is collisional, compressional. If it's a rarefaction, then it's tensional, it's pulling apart. So someone who is detecting earthquakes on the east coast of the United States, detecting earthquakes that are forming in the mid-ocean ridge, they always see a compression first, because out in the center of the ocean, the rocks separated, which is a motion, is a compression. So first motion studies. And so here's some visualizations of some different types of waves.